Let's begin with the following problem on static and kinetic frictions. Masses A and B have weights 40 newtons and 20 newtons respectively. Find the minimum weight of mass C, which is resting on A, to keep A from sliding if the coefficient of static friction between A and the table, so that is the surface between A and the table, is 0.25. So let's do part A first. So none of the objects are moving. So let's do the free body diagram for object B. Now the forces that are acting on object B are as follows. The first of all is its weight. We know it's 20 newtons. That's given right there. And then you have this tension from this cord or that string. This enables us to write down right away the value of the tension, which is 20 newtons. Now there is no acceleration, there is no motion whatsoever. So tension balances the weight. Now let's look at that object. Object A, and on top of which there is another object, C, and it is on a table surface. What are the forces acting on this object A? The first one is tension in this cord, the same tension that we have computed above. And then you have this static friction because we want to prevent sliding. So let's call that static friction F sub S. And then you have this weight. Now the weight that is acting on A is its weight, which is 40 newtons, plus some weight, which we don't know yet, of block C. So what we are going to write here is 40 plus an unknown weight of C. And of course you have normal force acting like that. None of the blocks are moving. So the forward force must be balanced by the backward force. So tension equals static friction. We note that static friction is given by an inequality as follows. Mu sub S times the normal force on a given object. So the maximum static friction acting on a body is given by the product of the coefficient of static friction, which is mu sub S, and the normal force acting on that particular body. And it cannot exceed that threshold, that maximum value. So writing this inequality here, it simply becomes mu sub S, which we know to be 0.25, that is the coefficient of static friction between this object and the surface on which it's resting. So it's 0.25 times this normal force on this system. Let's expand on this. Tension is 20 newtons, and that is the same as F sub S. So which are the conclusions we have determined from the following free body diagrams? So 20 newtons less or equal to 0.25 times the normal force. From this free body diagram, normal force equals 40 plus that unknown weight of block C. So you can simply write 40 plus W. That means 40 plus W is greater or equal to 20 divided by 0.25, or simply 80. So 40 plus W is greater or equal to 80. Now what that means is your W is greater or equal to 40 newtons. So that means the minimum weight, the minimum value for W that keeps A from sliding on the table is therefore 40 newtons. So that's the answer for part A. So the answer for part A is 40 newtons. Part B, if C, the smaller object, is suddenly removed off A. What is the acceleration of A if the coefficient of kinetic friction between A and the table surface is 0.15? So now things start to move. As you remove object C from the top of A would start to move to the right and B would start to move downward with some acceleration. What is that acceleration? So let's start with the free body diagram for object B. The forces acting on object B, again, its weight, which we know to be 20 newtons, and you have this tension that's pulling it upward from this cord, and it's now moving with some acceleration A. So that means the net force is downward, and the net force is given by 20 minus tension. So 20 minus tension equals the mass of this object B is the weight divided by gravitational acceleration, G. So 20 divided by G is the mass of B, where G is 9.81 meter per second squared, times the acceleration. So what I have done here is to apply Newton's second law to object B. So that's equation 1. Now let's look at object A. Object A does not have C on top of it anymore. So the forces acting on this object A is its own weight, which is 40 newtons. There is a normal force. Now it's moving, so there is a kinetic friction. There is a tension from the cord, and it is moving with some acceleration A. Applying Newton's second law, we see that the net force in the rightward direction, because that's also the direction of acceleration, is the tension minus kinetic friction. So tension minus kinetic friction equals the mass of object A, which is its weight divided by gravity, 9.81, times the acceleration A. Now, kinetic friction is given by the coefficient of kinetic friction, which is 0.15, times the normal force, and in this case the normal force is just the weight, 40, equals 40 over GA. So that is equation 2. Now you have equation 1 and you have equation 2. There are two unknowns, tension and the acceleration, and you can solve for the acceleration. As you add equations 1 and 2, you see that the tension goes away because T plus minus D is 0. So the left-hand side becomes 20 plus minus of that, so it's quite simply minus 0.15 times 40 equals, the right-hand side is 20A over G plus 40A over G. That is simply 60A over G, and you can solve for the acceleration. And when you run through the calculation, you get the following value for the acceleration, 2.29 meter per second squared. And that's the answer for part B. Let's look at a slightly challenging problem. Block A, that's this block, with mass 15 kg is pressed against block B with mass 90 kg. The coefficient of static friction between the blocks, which means along that line, is 0.4. Block B is on a frictionless surface, so that means this surface is frictionless. Find the minimum force F that was applied like that on A that is required to maintain block A from slipping down block B. There are a few things that we need to understand here. Now, because this surface is frictionless, the entire system will move rightward with some acceleration A. Another thing is that at the contact point between A and B, there must be some contact forces that's acting on both ways with the same magnitude. So the force, the contact force exerted on B by A, like that, must be the same as the contact force exerted on A by B, which goes like that. So let's begin with the free body diagram for object A. So that's object A. What are the forces acting on object A? The first one is, of course, its weight, which is 15 times gravity, because the mass is 15 kg. The other one is this force F that's being pushed or exerted on A so that it stays on B. And then you have this static friction that's acting like that on A so that it doesn't slip down block B. So that direction of that static friction is like that, F sub S. And the last one is the contact force exerted by B on A. And that will go like that. Let's call it N. I'm calling this force N, so it's some sort of a normal force that creates the static friction. And that normal force results from the contact force between B and A. And lastly, do not forget the acceleration of the system, A. So since the acceleration of the system is rightward, the net force is also rightward. And the net force is formed by two forces, F and N. So the net force can be written as F minus the normal force, and that equals to the mass of object A, which is 15 times acceleration. So this is just Newton's second law being applied. So this is a crucial result. Let's call it result 1. Another result is to equate the static friction with the weight. If A were not to slip down block B, these two forces must balance out. So we say static friction equals 15g. 15g being the weight of object A. But we also know from the definition of static friction, it must be less or equal to the coefficient of static friction times the normal force. And we can therefore write the above expression as quite simply just that. Mu sub s is 0.4 and normal force. Let's call this result result 2. Now let's look at object B. The forces acting on object B is its weight, which is 90 times gravity. And then you have the acceleration going that way. Of course, you have another normal force from the surface, the frictional surface, which is going up. Let's call that N subscript B. And do not forget the contact force from object A that's going in that direction, which is the same as the contact force from B on A, the normal force. Newton's second law would suggest that N equals the mass of object B, which is 90, times the acceleration, and that is result 3. Putting 3 in 1, we get F as 105A. And substituting N in result 3, we get 15g less or equal 0.4 times 90A. Since we're interested in the minimum value of F, let's substitute A in terms of F in this inequality, and that's going to give you 15g less or equal 0.4 times 90 times F over 105, which will give you the following inequality for F. F being greater or equal to 429 newtons. So this inequality says the minimum value for F that is required to maintain A from slipping down B is quite simply 429 newtons. And that solves the problem. Thanks for watching.